Okay, welcome back. We'll start the second session with Professor Alessandro Acquisti, who is the Trustees Professor of Information Technology and Public Policy at Carnegie Mellon University. He will talk about privacy technology and economics of personal data.
Thank you, Ginger. Thank you for having me here. Absolutely a pleasure. I will indeed be talking about privacy technologies, a specific type of privacy technology, differential privacy, and how they may impact our understanding of the economics of privacy and the economics of personal data. This will be what I like to call the hourglass style of talk. By that, I mean that I will begin very broad, talking about big, open, complex research questions. Then I will zoom in and get into one specific, much more narrow research question. And in so doing, I will be talking about some results we have recently published related to differential privacy, US census, and economic cost. And then near the end of the talk, I will open up again the discussion, trying to draw some broader implications from our results. Now, I've been working for about 20 years on in the field of economics of personal data, economics of privacy. For those of you who are not in the field, you may perhaps be surprised to know that the economics of privacy did not start with the internet. Already back in the late 1970s, early 1980s, scholars, especially Chicago school scholars such as Posner and Stigler, pioneered the application of economic thinking to privacy and personal data. Their research then somewhat fizzled out. There was not much new work until the mid-1990s. And then in the mid-1990s, people like Hal Varian, Eli Noam, Kenneth Loudon started working again in the field. And then, of course, with the advent of the World Wide Web and the internet, the field started growing very, very rapidly. So much so that in 2016, I had the honor of working with my friends Curtis Taylor and Liad Wagman in writing a review of the economics of privacy for the Journal of Economic Literature. It is remarkable that although that paper, that review is just from 2016, which is about 7 years ago, in a way, it's already obsolete because so much has happened in the last few years. And in fact, we have seen in the presentations this morning evidence of the growth of the field, a remarkable growth of the field, almost exponential growth in terms of economic research attention in the last few years. And in a way, this is wonderful, right? For someone who has been working in an area for a while to see it exploding is really beautiful, and I am super happy. At the same time, I also have added the opportunity to spend some time looking back at the field, thanks to an invitation by two other of my friends, Catherine Tucker and Avi Goldfarb, that I'm sure most of you know very well, because they organized last year two seminal events at NBER. One event was a workshop on the economics of privacy. The second event was a tutorial for PhD students on the economics of privacy. And as part of the tutorial, they asked some of us to present and to write some piece related to the economics of privacy. So the piece I ended up writing, which is not out yet officially, but if you're interested at all in some of the key features that I'm about to describe in the next few seconds, you are welcome to send me an email and I will be delighted to share with you. My piece ends up being an analysis and a friendly critique of where this field has been going in the last 20 years. So hence the title, Economics of Privacy at the Crossroads. In this piece, I make the argument, the following argument, and which explains this image of a scale, of a balance. The way the results for the economics of privacy have been used in the public policy debate around privacy frames, and I believe problematically so, frame the debate in terms of two opposite and mutually exclusive outcomes. Either we have more data or we have more privacy. Essentially, we have to make a choice between these two mutually exclusive outcomes and scenarios. If we have more data, we are going to have more economic benefits, innovation, matching, to play along Dirk's presentation from a few minutes ago. If we have more privacy, well, we have more autonomy, dignity, freedom. However, we have economic costs, opportunity costs in the terms of losses of the benefit we would have otherwise obtained with more data. And I would say that much of the empirical work in economics of privacy is focused on the benefits of data and on the cost of regulation. And what I claim in the NBR piece, which is about to come out, is that we should actually scrutinize more this assumption of more privacy versus more data being antithetical public policy goals and public policy outcome. First of all, we don't know enough about the underlying downstream cost of privacy invasion. Second, although it is undeniable that great economic value is being created from the collection and analysis of consumer data, I argue that we know much less about the allocation of that value, to what extent the value accrued for consumer data is then returned back to the different stakeholders in the economy, the consumers, the publishers, the merchants, and of course, the intermediaries, the matchmakers, again, to refer to Dirk's language. And finally, are more data and more privacy truly, inherently, and systematically antithetical? Can we in fact have the cake and eat it too, thanks to the usage of privacy-enhancing technologies? Long this morning was referring to differential privacy, federated learning, homomorphic encryption. And indeed, this is now the narrow part of my talk, where I focus on a specific study that we have conducted about the extent to which the deployment of privacy-enhancing technologies into data creates downstream economic cost, and can we quantify them? So the piece came out in Science a few months ago and focuses on a specific type of technology, differential privacy, and on a specific application, US census using differential privacy. Differential privacy, in a nutshell, I will not get into a detailed economic description, mathematical description of it, but in essence, is a technology which offers organizations a way to share, even publicly share and disclose data sets, which may contain personal, even sensitive information in a manner that is actually guaranteed statistically to protect individuals' data. And it works by adding noise to the data, so much so that the outcome of any data analysis will nearly be equal, regardless of whether a specific individual and her specific data are or are not in the data set. Now, the US Census Bureau, under the leadership of John Abbott, an economist well known to many of you, started discussing differential privacy several years ago, and then started applying differential privacy to US Census data, attracting the attention and the welcome attention of privacy scholars, but also attracting some attacks from demographers and other communities. Well, in a way, whenever we add noise to the data, as economists, we know there is no free lunch, right? We are degrading to some extent the utility of the data. So we are traveling somewhere on this data privacy, data utility trade-off. The key question is how much we are losing in terms of data utility. And if you look at the vehement and rather aggressive attacks that the US Census deployment of differential privacy has attracted, you will be led to conclude that the damage in terms of lost economic utility is very significant. So much so that Alabama even sued the federal government to stop the privacy initiative that the US Census wanted to enact. So our research question was, well, to what extent we can quantify the cost in terms of data utility caused by differential privacy? And can we compare it in order to give some ballpark estimate? Can we compare it to the cost of other forms of data uncertainty? Because what we argue in the paper that we just published is that the current debate is focused on the cost due to differential privacy, to the fact that differential privacy adds noise. So here we have a data point and we add the perturbation. So we increase the confidence intervals to the data point due to differential privacy. And that, in a way, is the top of the iceberg. But beneath that iceberg, there are many other sources of data uncertainty, which have nothing to do with differential privacy, and they already exist. And the census knows about them. Some of them are theoretically quantifiable, at least in statistical terms. So data error due to sampling sampling errors, measurement errors. Some is unquantified and probably unquantifiable. But if we focus on the quantifiable one, can we compare the data loss utility due to data errors to that of differential privacy? And that's exactly what we did. So we focus on one application of US census data, Title I education funding. Essentially, many US agencies use census data for many important purposes. One of those agencies is the Department of Education. We use census data and specifically the estimates of the number of children in poverty across the United States and across school districts in the United States. And those estimates are used to decide funding allocation to school districts. Okay, so very, very important application of US data. And what we did was to first simulate the impact of data error, so not data differential privacy, but the existing data error on Title I funding allocation. So we look at census published distribution because census knows there is error and they can even provide the distribution of the error. Of course, they cannot quantify precisely, but they have a distribution of that error, which we use to calculate the impact of data error on the allocation of funding to different school districts. Second, we simulated the impact of instead adding differentially private noise to the same underlying estimates. And we use two different epsilon parameters, 0, 1, and 1. A technical description of epsilon would probably elude my 15 minutes with you, but in a nutshell, the epsilon captures the degree of privacy guarantees that we can give to our differentially private algorithm. The smaller the epsilon, the more privacy we have, the more the data is protected. 0, 1 is loss of privacy. Even epsilon or 1 is already loss of privacy because in many practical applications, the epsilon use is about 15 or 20. So we are talking about strong privacy guarantees here, strong and stronger. And finally, we compare the misallocation. And by misallocation, essentially, we refer to the distance between the theoretical ground truth of how much a school district will get in terms of funding each year, and what it will get under differentially private noise and under calculations of the noise in census data. We compare between the two, and we try to estimate how differential privacy, how the loss in data utility due to differential privacy compares to the loss of utility due to underlying data error. And in a nutshell, the answer is the cost of data differential privacy is very, very small. It's at the margin of much larger cost of data error. And how much? Well, here in this graph, let me skip this slide. In this graph, I give a visual representation of the different dimensions we're talking about. What I have on the bar, the horizontal length of the bar, are all of the $11.7 billion that are used under Title I grants to and sent to different school districts in the United States. And that's entire length of the horizontal bar. The part in blue, about $1 billion, that's the misallocation due to the error under our estimates, okay? So it's pretty significant, it's close to 10%. And now I'm about to show you instead the misallocations due to differential privacy. There it is, 50 million under strong privacy and 0.7 under even stronger privacy. So in a nutshell, the point here is that, yes, there is no free lunch. Differential privacy does add some error. As a matter of fact, that error is also unequally distributed across different districts. So it tends to penalize larger school districts rather than smaller school districts. It also penalizes certain students with certain socioeconomic background or even race, such as African-American students as opposed to white students. There are statistical reasons for that. So yes, there is some misallocation, but the misallocation pales is very small compared to the misallocations due to data errors. And you know what? We can actually use some money to compensate the noise and the data loss due to privacy. And the amount of money we need to invest is not that large. In fact, in the paper, we also suggest a number of policy changes that can be enacted in order to, in a way, offset the potential damaging effects of differential privacy. So, to go back to the bigger picture that I promised you when I told you about this hourglass style of talk, In a nutshell, we find that these misallocations due to differential privacy occur on the margin of much larger misallocations due to data error. And we can pay for them. And the bigger point here is that privacy technologies such as differential privacy may in fact offer ways to protect privacy while minimizing data utility losses at relatively low cost. Thank you very much for your attention.
Thank you, Alexandra. And it's hopeful to know that technology can solve the problem created by technology. So far, we have